So the first speaker of the afternoon will be Alan Sokal from New York University, and he will talk again an introduction to Maya expansion.
Thank you. I should say this is a sad day for me, as it is for a lot of us. Although I didn't know Pierre well, he was always very, very helpful to me whenever we met, very kind, even when I was completely out of my depth in combinatorics. And the last time I saw him was a year ago in Montreal, where he organized a wonderful school and workshop on precisely this subject of combinatorics and statistical mechanics. And among other things, he very patiently tried to teach me to cross-country ski, without very much success, I must say. And so when we decided to organize this particular workshop, my co-organizers and I immediately thought of Pierre and Malek as the two perfect co-organizers, one coming from a combinatorics background, one coming from a mathematical physics background, but both being fluent in the languages of the other. And they've done a great job of organizing this workshop, and it was a real shock to me when I heard, I guess it was a little less than 2 months ago, that Pierre was sick, and then even more of a shock when I heard a month ago that he had died. So I was looking forward to having Pierre in the audience right here and then having discussions with him afterwards, and unfortunately that's not going to happen. Okay, so what I'm going to do today is to try to give a survey talk, an introduction to the Mayer expansion from mathematical statistical mechanics, mostly for the non-physicists in the audience. Most of what I'm going to say is fairly well known. There may be a few things that are new, or new ways of looking at things, which you can find in a paper by Alex Scott and myself, which is linked to on the Newton website. It's a little funny because, as some of the mathematical physicists in the audience know, for the first 25 years of my career as a mathematical physicist, I was extremely scared of the cluster expansion and Mayer expansion, and I did everything I could to avoid it, and some of my best work was about circumventing the cluster expansion and finding other simpler ways to do things. But then recently I became seduced, and so, well, you'll see, hopefully you'll get seduced too, because it is actually a very beautiful combinatorial as well as physical structure. So what I'm going to be talking about is, from a physical point of view, the repulsive lattice gas. So it just means, let me define that first. But you'll see a special case of this repulsive lattice gas is the independent set polynomial in combinatorics, independent set polynomial of a graph, where this word has a double meaning. Independent set means independent sets of vertices, or stable sets of vertices in a graph. So I'll come back to that. So what is the repulsive lattice gas? You have some state space. Well, let me just call it this. It's the underlying set. Let me call it that. The underlying set X, which for me will be a finite set, but it can be more general. This is the space where we're going to throw down particles. And then we're going to throw some finite number of particles into this set X, 0 or more particles, and they're going to get certain weights, which are defined by two things. There will be a vector of what physicists call fugacities, or activities. So for each point in the space, in this finite set, there will be a fugacity W sub x, and I'll assemble those into a vector W. And in general, those can be complex numbers. We'll see that's important, although for many applications, you want them to be positive real, because if these fugacities are positive real, then the things that I'm going to write down will have interpretations as unnormalized probabilities. So probabilists would like these to be positive real, but I will take them to be general complex. And then we have a two-body Boltzmann factor that measures the weight that a pair of particles to get. So there will be, that's Wxy, and it's symmetric. That's the same as Wyx. And if you want, you can assemble those into a matrix, W tilde. And then here is the partition function for the repulsive lattice gas. So it's a function of the fugacities and the two-particle weights. And I'll write it like this because we usually think of the two-particle interaction factors as parameters, and we think of the fugacities as the variables. And so it's the sum, n equals 0 to infinity, 1 over n factorial. There's one of my friends who says that n factorial should be pronounced n! Anyway, so 1 over n factorial coming from basically from the fact that these particles are indistinguishable. And then we have sum over ways of placing these particles x1 through xn in the set X. And they need not be distinct points. There's a sum over all of the ways you can place those guys in X. And then there are two types of weights. There's product I equals 1 to n Wxi. Those are the weights for each particle. And then there's a weight for each pair of particles. So 1 less than or equal to I, less than n, less than j, less than or equal to n. So for every pair of distinct particles, there is this two-particle Boltzmann factor. So that's the definition. Of course, you can think of it as a formal power series if you want, but we physicists want to think analytically. So you need this to be somehow convergent. I will take the simplest case. It's not the only case that you can consider, but I will consider the two-particle interactions to be repulsive, that is to say, lying between 0 and 1 for all xy. Oh, by the way, I should say this wxy, wyx, that includes, there's a diagonal term too. You have to say what wxx is. If you have two particles sitting on the same site, they might interact also. What?
So you want those included in the product?
No. You see, these particles the particles are numbered, right? You have billiard balls numbered 1 through n, and you put them there. A particle doesn't interact with itself. I mean, if it did, you could just throw it into its fugacity anyway. Particle doesn't interact with itself, but pairs of particles, if they're on the same, they interact wherever they are. So in particular, if they're on the same site, you have to specify how much two or more particles interact if they're on the same site. Okay? Good. By the way, please interrupt with questions. I hate questions at the end. Ask questions during. Okay, so repulsive, of course, if the capital W's are 1, then the particles don't interact, and this is just a trivial exponential. But, so we're going to say they're repulsive in the sense that if you put two particles down, it will only depress the weight, okay? Once you have repulsive, then it immediately follows that this sum is convergent and defines an entire function, z of w is bounded in magnitude by exponential of the sum over all x in x of absolute wx. Entire function of the many complex variables. Yes?
So why is this repulsive and what would attractive be?
Attractive would be w's bigger than 1,
Oh, I see.
right? That's all. I mean, the language comes from physics, but if having two particles there depresses the weight, that's repulsive. If having two particles there increases the weight, it's called attractive. And you see, in the attractive case, you can have problems. What if x was just a single point? Then, so x is 1 point. Then the partition function would be sum n equals 0 to infinity, w to the n over n factorial, capital W to the n choose 2. And if capital W is bigger than 1, the sum is divergent. It has 0 radius of convergence, which is not a problem for Gilbert because he was working with formal power series, but it is a problem for me. So you don't have to assume something as strong as repulsive to get convergence. You can assume weaker things like stable, which means roughly that the interaction is repulsive enough that it's enough repulsive in some places that you can handle a little attraction at others. But I'm only interested in the repulsive case. Okay, so this is the general repulsive lattice gas. It's what I will call level 1, the most general level. Okay, a specialization of this is if, and that's what I'll call, well, which I'll call level 2. What if all the self-interactions are 0? That is, interactions. So if all the WXX's are 0, that means you cannot place more than one particle on a site, because it'll get 0 weight. So then, this partition function can simply be written as a sum over subsets of x, the places where you put one particle, and then the weights will be product x in A, the weight, and product over all unordered 2-element subsets of A, I not equal to J. Well, I'm sorry, let me call them xy, 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 w of xy. Okay? WXX equals 0 is what physicists call a hardcore self-repulsion. Self-repulsion, because it says you can't put more than one particle on a given site. Yeah?
1 over n?
The 1 over n factorial disappears because the set A, you see these are labeled particles, this is unlabeled. And because all of the n, I mean, if A has cardinality n, the n points are distinct. They're exactly n factorial ways of labeling these billiard balls that live on different sites. Thank you. Okay. And then, so that's what I'll call level 2. And then level 3 is when you further specialize so that the interactions between sites are either 0 or 1. That is either no interaction at all, that's 1, or totally forbidden, that's 0. WXX equals 0 for all x, and WXY is 0 or 1 for all xy. Then you might as well just think of this as the independent, and this is what we would call hardcore self-repulsion and hardcore mutual interaction. And then you might as well define, let x be the vertex set of a graph, and define the edge set to be the set of xy's such that wxy is 0. Those are the forbidden pairs. And then this is just the independent set polynomial of this graph. You define the graph gxe. Then this is the independent set polynomial, sum A in x, A independent or stable product. Because an independent set of vertices in a graph is any set that contains no nearest neighbor pairs. Okay? So this is exactly, the level 3 is exactly the standard independent set polynomial or stable set polynomial from combinatorics, except that usually combinatorialists will consider a univariate version where all the wx's are equal to the same number w, and then it'll be some polynomial that counts the number of independent sets of different cardinalities. But I think that both for mathematical purposes and you will see for physics purposes, it's much better to consider the multivariate polynomial that allows a different fugacity at each vertex. And then you can specialize if you want at the end to setting all the wx's equal to w. You'll see that this, considering this multivariate version, is much more flexible. You'll see, for example, it allows a very simple inductive proof of one of the theorems. Of course, and the key fact is that this polynomial is multi-affine. It's of degree 1 in each of the wx's separately. And that allows simple inductive proofs. Multi-affine, multivariate polynomials are in many ways much simpler than general polynomials in a single variable. Okay, so those are the three levels that I want to analyze. And it's useful to keep in mind these three levels because different techniques work at different levels, as you'll see in a second. Now, there are two major applications of this. I'm not going to talk about the applications. Other people later will talk about the applications. But the two major applications, the first one is the obvious one, where let's just look at level 3. It doesn't really matter. The graph is a large piece of a regular lattice, like ZD. I mean, this is the kind of thing that physicists think of when they think of a lattice gas. You have a big lattice and you throw down particles with some weights. That's the major direct application for physicists. And in such a case, of course, you would assume translation invariance, so then all of the wx's would be the same, and wxy would be a translation invariant function, so a function of x minus y. The second and more subtle application is what physicists call the polymer expansion, and various people here, in particular Roman Kotecki in the next talk, will talk about that. The point is that you start from some statistical mechanical model, not necessarily a lattice gas, maybe an Ising model or a Potts model or any model you like, living on some other graph, H, let's say, which would usually be a piece of a regular lattice. And then by various methods, you algebraically rewrite the partition function of that model as equal to one of these guys. In fact, it will be at level 3. It will be an independent set polynomial for what's called a polymer gas. The polymers will be some connected subsets of this graph H, where the model you're interested in lies. And then there will be constraints that are usually just saying that polymers can't overlap, or maybe they say that polymers can't get too close to each other. But there will be some kind of polymers, depending on what model you're working with, and some kind of constraints. And moreover, you will have fugacities, Wx for the polymers, that vary a lot from one polymer to another. In particular, you can have very big polymers, but usually the fugacities will decay exponentially with the size of the polymer, so that the big polymers have exponentially small fugacities. And then you have to analyze this polymer gas. So you build this polymer gas on some graph H, and then you have this graph G, whose vertices are the polymers in H, and whose edges are something like disjointness, that overlapping polymers are forbidden, or something like that. And that's the major application. So the talks of both Kotecki and Fernandez and probably some others will look at that application. But I want to stress that my philosophy is to keep separate the general theory of repulsive lattice gas and independent set polynomial from the specific applications. In particular, the mathematical physics literature sometimes defines a concept called an abstract polymer gas. Well, what is an abstract polymer gas? It's just the independent set polynomial on an arbitrary graph. But then they go and what I would call a vertex, they call a polymer. And what I would call an edge, they call the incompatibility relation, which is perfectly fine. You can use any terminology you want. But for me, that psychologically makes things harder because you're carrying in your mind this view of an extra level of structure, which is totally irrelevant for the general theory. So in this talk, a vertex will be called a vertex, and an edge will be called an edge. Okay, however, we do have to take one important fact from this second application. The second application tells you it's not sufficient to consider the case of G being a regular lattice or a piece of a regular lattice. It's not sufficient to consider the cases where all the fugacities are equal, because that will be radically false in the polymer expansion application. It's not sufficient to get bounds in terms of something like the maximum degree of the graph, because this polymer graph will be, every vertex, in fact, will have huge degree, because every polymer, even if it's only a single vertex by itself, overlaps some huge number of huge polymers. So you can't do things in terms of maximum degree. But what will happen is, if a vertex in the graph has high degree, then either it will have a small fugacity, or its many neighbors will have very small fugacity, and that will save you. So you have to look for hypotheses that will work in case 2 as well as in case 1. And that's what I'm going to describe now. Okay, so now the next thing to explain is why what's of interest to us is not really the partition function, which is after all an entire function in many complex variables, but what's of interest to us is log of the partition function. Now, first of all, the first thing to notice is in any of these 3 levels, it doesn't matter. The first term in this formal power series is 1, right? That comes from putting down no particles, right? So z is always 1 plus stuff. So therefore, log z is well defined at least as a formal power series and is 0 plus stuff. And moreover, not just a formal power series, these are analytic functions on basically ck, right, if x has cardinality k. So log z is analytic in some neighborhood of 0 fugacity. So this formal power series is convergent in some polydisk. But it's important to know how big a polydisk, and here's why. In most applications, in either case 1 or case 2, we're not interested just in a single graph. We're interested actually in a sequence of bigger and bigger graphs. For example, in case 1, we'll be interested in bigger and bigger pieces of the regular lattice. In case 2, we'll be interested in the polymer expansion built on bigger and bigger pieces of the underlying regular lattice of the other model. And we're interested in taking the infinite volume limit. And what that means is it's not z that's going to have a good infinite volume limit for this sequence of graphs. It will be what physicists call the free energy per unit volume that has a good infinite volume limit. So that means is that these z's are going to be based on some sequence of graphs, let me call them Gn, and then we'll divide by the size of Gn, let's say the number of vertices, and limit and go to infinity. And in good cases, that will have a good infinite volume limit. And we're interested in what its analyticity properties are. It may be analytic up to some point and then fail to be analytic, and where it fails to be analytic is the phase transition. And so what you see is, so we want some quantitative bounds. Here I said some neighborhood, but we want some quantitative bounds on how big a neighborhood can log z be analytic. In other words, how big a neighborhood can z itself be zero free? Because it's only the zeros of the partition function that can cause singularities of the log of partition function. So we're interested in quantitative bounds which will be uniform in the infinite volume limit. So if we take something like bigger and bigger pieces of a regular lattice, we want bounds that are independent of the size of the lattice and depend on only local things like the maximum degree of the vertices or something local about how strongly a given vertex is coupled to other vertices. So that's the explanation for why we want to study log z, and therefore that's the explanation for why we want to look for zero-free polydisks in c to the x for this partition function. Okay, now I'll tell you what the Mayer expansion is. The Mayer expansion is an expansion for log z, which is, I believe, due to the physicists Mayer, or maybe it's Mayer and Mayer. It's Mayer and Mayer, right? They're two. The famous one is Maria, and the less famous one is her husband. whose name I don't remember.
Was Joe,
What?
Joe, and he was a chemist, I think.
Oh, I see. Oh, that's why he's less famous. But she was a nuclear. But she was a nuclear physicist. But I guess in the 40s you got famous being a nuclear physicist. But anyway, the two of them made a fundamental contribution to statistical mechanics, I guess I think it was 1942, somewhere around then. And it's the following. You have this lattice gas. So this is the Mayer expansion. You have Z is sum n equals 0 to infinity, 1 over n factorial, sum x1 through xn in x, product of the fugacities, and product of the two particle Boltzmann factors. Okay? And I'm going to derive an expansion for log z. For now at the formal power series level. So it'll be formal power series in the little w's. And what am I going to do? I'm going to add and subtract 1. So I will write w of xy equals 1 plus f of x and y. Which of course, remember the w, capital W's are somewhere between 0 and 1. So the f's are between -1 and 0. That will turn out to be crucial later, but not right now. Okay, now, so I write this product of 1 plus f. Okay, so what is this? And remember, this product runs over I less than j from 1 to n. So I can just write this as sum over all graphs G, I'll write script Gn, so these are simple graphs on the vertex set 1 through n, and then product over edge I pairs ij in the edge set of G, f of xi, xj, right? I mean, this is just a rewriting of what you get when you expand out the product over pairs ij, and the graphs, the edge set of G tells you which guys are getting the factors f. Okay? So that's fairly trivial. Now, log z will turn out to be the same sum, but instead of looking at all simple graphs on G, you just, on 1 through n, you looked at connected simple graphs. Oh, sorry. So a simple graph is no loops and no multiple edges. So a simple graph is what most people call a graph. Okay? So just there are 2 to the n ways you can make, I'm sorry, there are 2 to the n choose 2 ways you can make a graph on the vertex at 1 through n by putting edges or not putting edges. That's what I'm summing over. Yeah?
You allow loops. Maybe you mean looped self-loops, do you? You allow loops.
Okay, we need translation dictionary. What mathematicians call loops, physicists call self-loops. What physicists call loops, mathematicians call cycles or circuits. Sorry for yeah, we really need a translation. So, which somebody should publish. You know, translation dictionary, mathematicians here, physicists here. Okay, so it's all clear what the notation means?
What is the answer then? No loops?
No. Simple graphs are graphs with no loops or no self loops and no multiple edges. Okay? There are exactly 2 to the n choose 2 of them, right? So is it clear what I mean by? It's what most of you call a graph. Okay? And Cn are the connected ones of those. And why is this true? Well, the easiest way is let me define on the space of all the GNs, of the script GNs, let me define weights as the weight of a graph is sum over x1 through xn. Let's see, right? So so GN are graphs with labels 1 through n, right? So I can on this graph put particles put a particle x1 on point 1. I mean, so, you see, these guys are not, this graph is not built on the set x. This graph is built on the abstract set of labels 1 through n, the labels on the billiard balls. And then this, oh, I'm sorry, I shouldn't call this W. Let me call it script W. The weight of one of these abstract graphs will be.
And these x's, they come from the set.
Exactly. Given an abstract, G is a Mayer graph. Okay. Given an abstract Mayer graph, it's a graph on the vertex set 1 through n with labels 1 through n.
Yeah, but I could see so in the summation, x1, no, downstairs. x1, xn comes from.
No. Here there's no x's.
Downstairs. Last line.
Well, you're.
Last line.
Down.
The bottom.
No.
Where I haven't finished yet.
Yeah, but then you say in x. Shouldn't this be in?
No. This is if you want. These are mappings from the vertices of the abstract graph into x. You see, I have an abstract graph. I've divided this up into 2 levels. I have an abstract graph G on the vertex set 1 through n. And then to define the weight of that abstract graph, I sum over all ways of putting particle positions on this abstract graph, right? So I have an abstract graph. Here's n equals 3, okay? And then I will sum over with labels 1, 2, 3. And then I will sum over all ways of putting an x1 there, an x2 there, and an x3 there. So all maps of the vertex set of the abstract graph to the vertex set of my repulsive lattice gas model. Okay? And then I get a product of wxi's and a product 1 less than or I less than j less than or equal to n f of xi xj. Okay? That's the weight that I have.
The graphs have to be spanning there.
Where?
In the second, in the log.
It can't be because
The vertex set is always 1 through n. On the top line, the graphs are all graphs. And on the bottom line, the graphs are connected graphs.
but where does the graph enter now? Where does the graph enter in the definition?
You'll see, I'm rewriting this. So the point is, if I define W of G like this, then I have simply rewritten Z is sum n equals 0 to infinity 1 over n factorial sum over G in Gn, the weight. In other words, I've just.
But now at the moment, each graph on n vertices has the same weight.
No.
I think you forgot
It's
IJ.
ij, not a EFG.
What did I forget?
Maybe you have a product or ing, that this should be edges in the graph.
Oh, I'm sorry. Yes. Sorry. Absolutely. So this is ij's in the edge set of the graph. Sorry. Right up. The same as I have up there. Sorry. Okay? So all I've done is I've pulled out, I've reorganized the sum. So I put the sum on graphs outside, and everything else I call the weight of this abstract Mayer graph. Okay? And so I'm in a situation where I'm certainly not going to finish this talk in an hour, but anyway, it doesn't matter. Most of what I have to say you can read in the article with Alex. So I'll try to get to the stuff that isn't. Oh, when am I supposed to finish? At 3? Okay. I'm certainly not going to finish in 2 hours. Anyway, I won't write down the accent. Once you define W like that, it's obvious the W of the empty set is 1. W is invariant under relabeling of the vertices 1 through n. And W of a disconnected graph is product of the W's of the connected pieces. Therefore, you're in the situation of the exponential formula, which is actually a very special case of Gilbert's composition of species. It's the case where you're composing the species E with something else. And then it's a well-known fact, which I believe is actually due to physicists, that, at least in this case, that the formal power series for the log of the partition function will be given by the same thing, but you have connected graphs rather than all graphs. So that's the Mayer expansion. And so we want to know so the Mayer coefficients are these W of G, just the W of G's for connected graphs G. Yeah?
What is the Mayer expansion again?
So Mayer expansion is the expansion for log Z that you get. So the Mayer expansion is log Z is sum n equals 1 to infinity 1 over n factorial sum over connected graphs on n vertices and the weights that I just wrote. Okay, this is the Mayer expansion. So far, I've just proven it at the level of formal power series. But we know it has to be convergent in some polydisk because Z is zero-free in some polydisk. I mean, this will be basically convergent up to the first zeros. It'll be convergent in any polydisk around the origin, which is zero-free for the partition function. But we want to know things like what can we say in general about the Mayer coefficients. For example, how do they, I'm sorry, so the Mayer coefficients are, you extract all the little w's out of it, right? I mean, and then the coefficients of the various monomials in the little w's, those are what are called the Mayer coefficients. And we want to know how the Mayer coefficients depend on the order, right? I mean, so if you want, you can write this as sum over multi-indices n, indexed by capital X, C sub n of the little w and big W times the monomial x to the n.
Okay.
Yeah?
Where does the irreducible come in?
Irreducible?
Yes.
I didn't use the word irreducible yet, or at least I don't think I'm going to.
No, I'm just usually in statistical mechanics, the Mayer expansion reduced to sum over irreducible graph. In other words, you don't have this
people. Yeah, there may be another language that I have to. I think the answer. I think what you're getting to is you can go further and deal not with log z. You go beyond log z and you take some kind of Legendre transform, and then you will get a similar sum where you sum not over connected graphs but over two connected graphs, which physicists would call irreducible, I guess. Yeah, question?
Started with W and replaced it by F, 1 plus F.
Yes, exactly. That's the key thing.
My question is, if you take again F and replace it by 1 plus H.
I mean, if you keep going, well,
what's the reason?
Well, obviously, the reason for writing W of 1 plus F, why is 1 special? W equals 1 is no interaction.
Why cannot you do the same with F? Replace your F by 1 plus...
Well, that would be equivalent to starting with writing W as 2 plus something.
So what did you gain by this?
Well, 1 plus something is, W equals 1 is no interaction.
I think
Yeah?
the first sum is over all graphs, and now I arrived at something which is over connected graphs.
Right, that's the key thing. And you see, the point is, since W equals 1 corresponds to no interaction, F equals 0 corresponds to no interaction. So F is kind of the strength of repulsion. F equals 0 is no interaction. F equals minus 1 is full repulsion, full exclusion. Yeah?
Are we at level 3 now?
We're at any level, 1, 2, or 3. We're at level 1, 2, or 3. This is totally general so far. Okay? So you can write it as sum over multi-indices, and with these things here, and these things here are called the Mayer coefficients. And so we're interested in two things. We're interested in general properties of the Mayer coefficients, and we're interested in specifically proving under reasonable hypotheses, by which I mean kind of local hypotheses, the convergence of the Mayer expansion in some polydisk. And by the way, let me just remark that if you look at rho x, which is wx d dwx log z, on the one hand, rho x can be called the density at x, because if you look in the probabilistic case where the w's are positive, it's actually the mean number of particles at x. And on the other hand, because we know that log z is written as a sum over graphs, this wx ddwx will be as a sum over rooted graphs, where the root must be mapped to this particular point x. Because it's as we saw already in Gilbert's talk, it's sometimes
Rooted connected graphs.
sorry, yes, of course, rooted connected graphs. Right. So it's sometimes more convenient to work with the rooted ones. Okay. So general properties of Mayer graphs. The most important one is the alternating sign property, which is that for any repulsive lattice gas, so it has to be repulsive, but other than that, we're at the most general level 1. It says the signs alternate. So -1 to the cardinal, to the total value of the multi-index, -1, Cn is non-negative. So all of the first order Mayer coefficients are positive, all the second order ones are negative, and so on. Yeah?
Could you repeat again what it is major coefficient?
This here, oh, sorry, this wasn't W, this was W, right? W to the n, sorry. So this here is some big formal power series in the little w's. You extract the particular monomial, and then its coefficient is the corresponding Mayer coefficient.
The coefficient doesn't depend from W, small w.
Oh, sorry, of course. Okay. Thank you. Sorry. Okay, so the alternating sign property says that the Mayer coefficients alternate in sign, and you can also control the first two derivatives with respect to capital W. After that, there's no general control. But you can control the first two derivatives. And I think I think I just don't have time to show you the proof of it, but it depends on a very important lemma and identity due to Penrose, not the famous Penrose, but his brother, Oliver Penrose, a statistical mechanician.
You mean the famous Penrose?
Well, for us, the famous Penrose. For us, the famous Penrose, but not if you count how many popular books were sold. And where's the chalk? Here's the chalk. Yeah. So I will just state the identity and the inequality that comes from it, and omit not just the proof, but omit explaining the combinatorial background, except I would just say for the combinatorialists, please look at the Penrose lemma, which you can see in my paper with Alex Scott, because I think there may be more interesting combinatorics there to be discovered. And what it says is take a graph, I'll call it H to not confuse it, we have so many graphs already. Take an abstract graph H, and let's have some some edge weights, Z sub E. And in H, I will consider two families of sets of edges. I will call T is the edge sets of spanning trees, and C is the edge sets of connected spanning subgraphs. So obviously the spanning trees are the minimal connected spanning subgraphs. Of course, I should have said H is connected. Otherwise, both of these would be empty. And I want to consider the polynomial CH of Z, which is the generating polynomial of connected spanning subgraphs. So sum over A's in the connected product of those edge weights. Because that's the kind of thing that comes up in the Mayer expansion, where in the Mayer expansion, the graph H will just be the complete graph Kn with particular attributions of x1 through xn on it, or eventually summed over. And then you will get things like this, where the z's are the f's. And it's crucial here that the z's will be between -1 and 0. And in fact, because you saw, remember I showed you at the beginning, an attractive lattice gas, the partition function might not even be well defined. It might have 0 radius of convergence. And so or even if it doesn't have 0 radius of convergence, it could be badly behaved in the limits we're interested in. So repulsive is important here. So we have this, and now we're interested in trying to prove the convergence of this Mayer expansion. And the traditional way is you bound this stuff, right? You put absolute value everywhere and bound this stuff. Okay? Well, if you just put absolute value everywhere and bound this stuff, you're screwed. And why are you screwed? Because how many connected graphs are there on n vertices? Well, for n large, nearly every graph is connected. So you have almost 2 to the n choose 2 connected graphs. So roughly 2 to the n squared. And that is much bigger than n factorial. And so so the sum just won't converge if you just bound everything naively. And that's a reflection of the fact that if you don't use the repulsiveness, you really are screwed. And so how do you get out of it? You obviously have to do some partial resummation of this Mayer expansion to exploit the alternating signs inside, the alternating signs all over. In particular, the alternating signs when you're summing different graphs with the same number of vertices, right? And the way you control it is with this beautiful, or one way to control it anyway, is with this beautiful identity and inequality due to Penrose in 1967, which is that so first I'll write the identity. The identity is there exists a way, in fact many ways. Combinatorialists have studied this and have found many different ways of doing it. There exists a way of mapping the trees into the connected graphs such that for every tree you map it up to for every tree you map it to something bigger, to some connected graph containing it, possibly itself, possibly with more edges. And the complex or anti-complex of connected spanning subgraphs can be written as a disjoint union of the Boolean intervals t to r of t. So the Boolean interval between two sets are all the sets that lie between them in the inclusion order, including, the closed Boolean interval. And the point is this is a disjoint union. So this is a way of cutting up the sum over connected graphs into Boolean intervals whose bottoms are the trees. Okay? Once you have that, then you immediately get the Penrose identity, the sum over all connecteds. Let me just write z. You understand what I mean when I write z to the a, right? It means product of the z, e, and a. I can decompose this as sum over trees. Everybody in the tree gets a weight a. And then all of the edges between t and r of t are optional. They can be put in or not put in totally independently because this is a Boolean interval. So then I get, so let me call these capital T, z to the capital T, and then I get just 1 plus z to the r of t minus t. Right? You understand what I mean by this notation? Z to the t means product e and t, ze, and so on. Okay? So once you can write it as a sum over trees where every edge in the tree gets its weight, and every edge between t and this guy above it, r of t, gets weight 1 plus z. Okay, so this is what I'll call the Penrose identity, and you'll hear more about it tomorrow from Aldo Procacci. The Penrose inequality is if these z's lie between -1 and 0, then you can just bound this in absolute value, and you get ch of z in absolute value is bounded by the sum over trees of absolute z to the t. The generating polynomial of connected spanning subgraphs is bounded above by the generating polynomial of spanning trees, provided that you put the absolute value of z in place of z. And now we've tamed the 2 to the n choose 2 divergence, because the number of trees is n to the n minus 2, which is basically like n factorial. It's n factorial e to the n. And so the traditional way of bounding this Mayer expansion is based on bounding all graphs by tree graphs, and then summing over these things, which you then actually get a non-zero radius of convergence. Now, and moreover, this Penrose lemma is also crucial for proving the alternating sign property. So this Penrose lemma actually plays 2 roles in this theory. Now, I'm running out of time. As I said, there's the traditional approach to bounding the Mayer expansion based on using directly the graphs and the Penrose lemma, and I don't have time to sketch more details, but I think Aldo will. The alternative approach is due to Debruchin, mathematical physicist in the early 90s, which I find incredibly beautiful. In fact, the only reason I even dared to look at the cluster expansion was that Debruchin's proof is so simple. And Debruchin says, look, instead of proving explicitly that the Taylor series for log z is convergent in a given polydisk, and then deducing from that that if log z is an analytic function, then obviously z is non-vanishing, do the reverse. Find directly a polydisk for which you can prove that z is non-vanishing, then log z has to be convergent in that polydisk. And so Debruchin's method, however, doesn't work in the general level 1, or at least it's an open problem to extend it to level 1. It's only good for level 2 or 3. That is to say, you do not want multiple occupation of a site. Yeah?
So you are saying that the radius of convergence of the Mayer expansion of log z related to the zeros of z.
Yes, right, exactly. The singularities of log z are precisely the zeros of z.
Why isn't it the case that it could be possible that z is becoming infinite?
Because z is an entire function. Remember, the repulsiveness assumption at the beginning proved that z is defined in the entire complex plane and is bounded by an exponential. So z itself has no singularities. It's only log z that can have singularities. So Debruchin's method is an inductive method, induction on the vertex set X, which allows you to prove inductively that a given polydisk in complex space is zero free. And it's a 3-line induction. Let me see if I have time. 2 minutes? Can you give me another 2 minutes? And what? I started 5. Okay. So let me see if I can prove. So the point is, first of all, for every subset of X, you define z lambda in the obvious way, where the sums are restricted to lambda. But it's equivalent to just set the fugacities outside of lambda to 0. It's the same thing. Okay. So you define these z lambdas, and of course, it's a multi-affine polynomial because we're in level 2 or 3. And for simplicity, I'll show it to you for level 3, but it generalizes to level 2. In fact, generalizes easily to level 2, although, as Roberto will remember, it took me about a year to find the easy generalization. So the important thing is z lambda of w. Now pick a vertex x in lambda. Either it's occupied or it isn't. So if it's not occupied, you get z minus x. And if it is occupied, you get a wx. And then not only is x excluded, but all the neighbors of x are excluded, because we're in level 3. So you subtract out the extended neighborhood of x, take out x and its neighbors, and you get that. So this is the fundamental identity, which allows you to do the inductive proof. So here is de Bruijn's theorem. Can I do this fast enough? So, quick. So, de Bruijn. Let R be a vector of Rx's greater than 0. That's the radii of your polydisk where you're purporting to prove that Z is non-vanishing. And suppose there exist constants K, so set of Kx's, such that 0 is less than Kx less than 1 over Rx for all x. These will be certain bounds. You'll see later what rule. And the Kx's have to satisfy. Kx is greater than or equal to the product of the y's on its neighbors, 1 minus Ky Ry. It's a little weird, but it'll come out in the proof why this is so. You just do the proof, and this is the hypothesis you need to make it go. And it follows from this, then, for all finite subsets lambda, Z lambda of W is analytic in the polydisk.
Logarithm.
What?
Logarithm.
Say this again?
Logarithm.
Oh, sorry.
This one is
Thank you. Log Z is analytic. No, I'm sorry. No. Sorry. Z, but I put this word wrong. Non-vanishing is the word. Z is non-vanishing in the polydisk, and its logarithmic derivative satisfies the following bound in this polydisk, Kx over 1 minus Kx absolute Wx. So these K's are bounds for the logarithmic derivative. And moreover, for lambda prime inside lambda, you get a bound on the ratio of the partition functions for the different sets. It's bounded by product over x in lambda minus lambda prime, 1 over 1 minus Kx absolute Wx. Okay, that's the claim. Let me call, so this is the hypothesis. This is the key hypothesis here. This is conclusion star, and this is conclusion double star. And we're going to prove this by induction on lambda, on the cardinality of lambda. Okay, first thing to note is that for any given lambda, star implies double star. By integration, right, if you integrate, for all the difference between z lambda and z lambda prime is all the fugacities in lambda minus lambda prime get replaced by 0. So if you integrate those fugacities from 0, between 0 and Wx, you integrate this. That gives you a logarithm of 1 minus Kx Wx. You then exponentiate it and you get a 1 over 1 minus Kx Wx. Okay, so that's, then now here's the induction. So the induction is, I'm going to prove star. I'm going to do induction on the cardinality of lambda. So it's obviously true for the empty set. So assume that it's true, 1 minute, 2 minutes. Assume that it's true for all sets of cardinality less than n, and now consider a lambda of cardinality n, and take any x in lambda. And let's use the fundamental identity. Z lambda is z lambda minus x plus wx z lambda minus the extended neighborhood of x. Okay? So we can just call this A and call this B. So this is it's a linear polynomial, A plus BWX. We know everything about it we want of such polynomials we want to know, right? So that d log z dwx is b over a plus bwx. And in order to conclude any of these things, we need to bound b over a. That's the crucial thing. B over a, both bounds how big a disk you can get in Wx that's zero free, and it also, B over A also bounds how fast the logarithmic derivative varies. So we use hypothesis double star for the set lambda minus x. Right, so use double star for lambda minus x, and you conclude that B over A is bounded in magnitude by product over the y's that are neighbors of x but not x itself, 1 over 1 minus ky absolute wy, but the w's are all bounded by r, by the r's, so you get 1 over 1 minus ky ry. But 1 minus 1 over ky ry is by hypothesis less than or equal to kx. So you've shown that B over A is bounded by kx, and that's what you need to conclude star for lambda. And I finished in 2 minutes.
Okay, thank you very much. Any question?
Yeah, Bill, hi.
Well, this is a very lovely argument, but I think you can do it in level 1 just as easily. And the way to do that is to make the connection with the theory of species. You look at the exponential generating function for rooted connected graphs. That satisfies an equation, a closed form equation, and you can do a fairly simple estimate on that and get the result on level 1. And it's all natural in the sense that it sort of follows directly from the theory of species with no cleverness or
Right. Is that by bounding graphs, like in the traditional approach, or by doing an inductive thing a la de Rushin?
Neither one.
Neither one.
You don't need any graphs or trees or anything like that. You don't need any inductions. You just need to write down the one simple equation for exponential generating functions, and you get to level 1 right away.
Okay, I'd like to see that, because of course you can also imagine a version of this for level 1 where you need to bound not linear things, but various infinite power series.
The reason this particular apparatus doesn't work for level 1 is because it's saying, if you just divide both sides by z sub lambda, it's saying that the probability of a particle being there plus the probability of a particle not being there add up to 1. And of course, in level 1, you're allowing multiple.
Right. I mean, in level 1, there's a general identity generalizing this that allows all different numbers of occupation. You get a whole power series in the W's, and then but then instead of 2 coefficients, you have an infinite series of coefficients. And I was, there probably is some way of generalizing this to level 1, but I don't know how. But you're proposing maybe a different way of handling level 1 that would also be interesting. Let me mention it. So in the part of the talk that I jumped over was the traditional method, bounding trees. I showed you how to use Penrose's lemma to bound connected graphs by trees. If you then use the rooted version by looking at the density rather than log z itself, then the rooted trees satisfy a simple recursion, as you know, by the species stuff that Gilbert showed us. And therefore, you can actually find the optimal bound for bounding the Mayer expansion in level 1, which is basically the old condition of Kotetsky and Price generalized from level 3 to level 1. And at level 1, it's optimal. And the de Bruijn, I didn't show you that condition, but the de Bruijn condition is a little better than Kotetsky-Price. And now you see why de Bruijn as it stands is valid only for levels 2 and 3. And you're somehow exploiting more there. But I think it would be nice to unify these things more, as you say. So I would like you to show me this later.
My paper, so
well, yeah, you sent it to me, but I didn't read it yet. Sorry. Yeah.
Level 1 means that you don't need to have a hardcore self-repair.
Right. Level 1 is allowing multiple occupation on a site. Level 2 is single occupation at most of a site, but the interactions between sites and their neighbors can be hard or soft. And level 3 is single occupation of a site and total exclusion between a site and its neighbors.
So I think also via the Penrose form, via the Penrose identity, you can get a bound.
Right, I was going to say Aldo in his talk tomorrow will show you how, well, the Penrose, using the Penrose, you already get it for level 1. What Aldo's going to show tomorrow is by using Penrose more cleverly, you can get improved bounds.
Just maintain something there, because you throw away all that factor bounding by 1.
Exactly. So Aldo's going to show tomorrow how, if you're in level 3, you can use the Penrose technique that we used for level 1, but exploit the fact that you're in level 3 and get better results, which are actually better than de Bruchens.
But actually also in level 1.
You'll tell us that tomorrow, because I thought your method was only for level 3.
Probably.
Okay.
Other question? Oh, yes.
Yeah, hi.
May I ask, so this independent set generating function, it includes a monomer dimer?
Yes, because if you do it, if the graph G that you're interested in is the line graph of a graph H, and I can't remember what the physicist term for a line graph is, then the independent set polynomial on the line graph of H is the same as the monomer dimer model on H.
So are there analogous of this result for monomer dimer partition function?
Well,
there is this analysis case.
Well, this includes the monomer dimer as a special case. However, in the monomer dimer result, other things are true. You get much more analyticity than this.
That is not true for this. So my question
No,
is...
for example, the Heilmann-Lieb theorem tells you that in the monomer dimer case, if all of the fugacities have the same sign of their real part, let's say they're all in the right half plane, then the monomer dimer partition function is non-zero. So you have a huge region that's zero-free, much bigger than these regions where I'm getting quantitative polydisks of given size, whereas the Heilmann-Lieb theorem is a general theorem that proves a huge region regardless of what the graph is. There might be some ways of putting those two results together in a common generalization, but I don't know.
Oh, I think other question at the tea break. So now it's tea time, and if you want other questions, just go privately, and we resume. We come back at 3:30. So enjoy the tea.